Book, for example, is at least 10 or 15 years old. So what you're going to hear tonight is the future textbook. You're going to know the science that has just been released in the last 10 years. And I'm going to talk about this amazing structure, the human cell, and how it works. And I also told you that the cell and you have the same functions. Where you have an organ in your body, the cell has organelles that carry out the same function. So that this is a respiratory and digestive system. These are all structures in the cell. And the issue is, what we really want to find out is, where's the brain of the cell? Because up to just a few minutes ago, the conventional belief is the brain of the cell are the genes. But if I take all the genes out and the brain is still functioning, we have to look for an alternative understanding of how the cell works. So I'm going to start off and give you some very basic insight into the mechanism of how cells work, okay? And cells are very interesting. They're like machines. This is an example of a transmission out of my car. And what you can see, it's called an exploded diagram, because you can see all these intricate little parts that all come together and assemble together to make a functional car transmission. Well, the point about it is this. The cell is analogous to this for the following reason. The cell is actually a machine made out of parts, but the parts are proteins, not metal parts and gears like this. The cells are made out of protein parts. There's approximately 70,000 protein parts. So when you open up a cell and you start to take it out, you can start to find that the building blocks are proteins. This becomes very important, because what I want you to understand is, when you look in the mirror and see yourself, when you say, you know, brown hair, blue eyes, such a height, all of that is due to the protein. The protein provides you with your structure. And so the assembly of these parts. And the interesting thing about these machine parts is this. I can do a lot of the functions in a test tube. I can do digestion in a test tube. All I have to do is take the right enzymes, the proteins for digestion, put it in a test tube. It'll do digestion. I can do muscle contraction. I can take the actin and myosin, which are the contractile proteins, put them in a test tube and make them contract in front of your eyes. I can do respiration in a test tube. What I'm saying again, the cell is a machine. It's made out of parts. The parts interact with each other to create the complex thing we call life. Well, let's talk about the parts. As I said, there were 70 to 90,000 different protein parts that make up the human. Now, here's the interesting understanding about these parts. Of all the proteins, all of them are linear strings, just like this beaded string. Every protein is a beaded string. The beads are the subunits. The little beads are called amino acids. So when you go to the health food store and you're talking about buying amino acids, what are you buying? You're buying the little building blocks to make the protein. So what makes the difference between 70 to 90,000 different proteins? And the answer is this. First, they're all strings, as I said, so that's already a commonality. What's the difference? Two things. The length of the chain, how many amino acids are in the string, is variable from one protein to the next. And number two, and most importantly, the sequence of the colors which represent the different amino acids are making the characteristic of the protein. Now, it's hard for you to see how you get structure out of something that looks like a string of beads. So instead of beads, I'm going to use these as representatives of beads. These are little pipe fittings. I have three different, actually, shapes of pipe fittings. A 45-degree angle pipe fitting, a 90-degree angle pipe fitting, and a straight one. So three variations. And consider there are 20 different variations. I'm only showing you three. So here's the point. If I start to assemble these pipe fittings in a sequence, what you can start to see is I am creating a linear chain, but now it's not so flexible and floppy. It actually has a rigid backbone kind of structure to it. So as I start to assemble this, you can see I can create a structure. Okay? But here's what I told you. What did I tell you about what was making the difference between the proteins? The sequence and the length of the chain. So look, what if I take this apart and reassemble the sequence of amino acids in a different sequence? Do you think I'm going to get the same shape? So let's take it apart and we'll take a look at it and see what happens. So the point about it is this. You assemble the amino acids, you put them in a sequence, and the sequence determines what's going to happen. So I take the same amino acids, plug them in now in a sequence, but a different sequence than just we had a second ago. And as I do this, you can see the shape of this protein is not the same as it was the first time. Is that evident? Can you see that? I want everybody to understand it. Why is this important? What's the point? The parts of the proteins have structure due to the sequence of these amino acids. Okay? Number two, how can I get 70,000 different parts? And the answer is this. By creating a chain with a different sequence of amino acids for each different protein. So you saw that, right? So now the bottom line is this. I have this particular protein. And if I just made a body out of protein only, and that's all it was, then I would be a statue. Instead of made out of brass or bronze, I'd be a statue made out of organic building blocks called a protein. There's no life. Where does the life come from? That is the most important, exciting question. I made a machine out of protein, but what is life? Life is animation. Life is movement. And so therefore, where's the movement come from? Now I'm going to show you that. And it's simple, because this is the ultimate understanding of where life comes from. When I assembled these together, I connected them like poppet beads, but look, they twist. Because at the junction, they're not locked, so I can change the shape of this protein. I just made this one. Okay? Now I'm going to show you something. Let me show you two different shapes. And before I do that, I'm going to give you a little piece of information. The yellow ones at the end are going to be negatively charged. Both of them are negative. Why is this important? We'll go back to a very basic principle of science. When two like charges come against each other, what do? They repel each other. And two opposite charges, what do? Attract. So I'm going to show you two different shapes of the same protein by just twisting it. And I'm going to ask you to tell me which is the more stable of the two. Okay? Let's use this as shape 1. Okay? Now I'm going to show you shape 2, and then I want you to tell me which is more stable, shape 1 or shape 2. Shape 2. And the reason why? Because the two negative charges repel each other. They want to get as far away from each other as they can. So does this make sense that this is a stable shape for this protein? Okay, cool. Now, I have this protein in your body, and I said that this was negative at the end. And this is an environmental signal, and I'm going to talk about environmental signals. Signals are either other molecules or atoms or energy. Energy can be signals as well. But in this case, let's say it's a molecule. Let's say it's estrogen, a hormone. And let's just say that it's very positively charged. What's the charge on here? Negative. A negative? Okay, so if this is coming along and this is positive, what happens when two opposite charges come near each other? So all of a sudden you're going to find that there's a binding. This is where the estrogen binds to the protein. Now, this is more positive than this negative. So the question is this. What's the charge at this end of the molecule now? Positive. What's the charge at this one? Now, the question is very simple. Is this shape of the molecule stable, or is this one more stable? Now, this is so fundamental. I want you to understand how critical this is. You understood that there was a shape, that if I have this molecule on, let's say I take this molecule off, what's the shape going to do? It's going to open back up like this, right? And then if I put the molecule back on, what's the shape going to do? Close. Well, you just told me there were two shapes that were stable, and the difference is when I add this signal, I go from one shape to the other. Does that make sense? Well, that is where life comes from. Life is movement of the proteins. The proteins move, and when they change shape, they can do jobs. So if I have work, I can have this thing do a job. By opening and closing, that would be its job. So you can say, well, what kind of jobs are just like simple movements? I'll give you a simple one. Let's say I'm a protein, and that this is the signal molecule, and I stand like this, and when the signal molecule hits in my hand, I go like that, and I let go of the signal. What happens if I let go of the signal? What's going to happen? I'm going to go back. And then another signal comes in my hand. Then what am I going to do? Go like this. And you say, well, that's a nice, simple movement, but what does that have to do with it? Well, if your house is on fire, and you have a bucket brigade, and I'm a protein in the middle, and somebody hands me the bucket, what am I going to do? Pick it from here and pass it to the other guy. Well, the point about it is very simply this. Proteins provide for my physical structure, but proteins can change shape when a signal binds to that protein. So all of a sudden it says that a static protein could just be sitting here, but the moment the signal shows up, the protein does something. Well, that something is hooked or actually used to do a job in the cell. So what is digestion? Here's an enzyme. It stands here. Here's the food molecule, and it gets caught in my hand, and I bring it together, and I rip it apart. That's all it is. Ripping apart. Digestion. So the bottom line is this. You're a machine. The structure of the machine is due to the protein parts. The proteins are all these linear chains made out of amino acids. That the final structure is due to the sequence of the amino acids and the charge. That's this critical part. When I balance the charge, the protein is stable. If I change the charge, the protein changes its shape. It's simple, but it's